going on in the next 50 minutes, even less, 30, 40 minutes, I will give you an overview of what biomedical engineering is bringing to mechanical engineering. Okay? Let's start with a recalling, which many of you may have read the concept of mechanics. That's what we study when it comes to engineering in the field of mechanical mechanics. So we start from kinematic, static, and dynamic, where kinematic is the study of things which move. Static, I'm sorry, I can use this lecture in year one.
Yeah.
It was the lighter version. And, then you can make comments and tell me how the perspective changed after 3 years. Discussion on the same lecture. So, kinematics, static, and dynamic are the three branches of physics which we use when we study mechanics. So, static is the study of forces which they balance themselves. So, if I stand on this table, till I will not break the table, this is static. If I study the motion of a body into a space, that's kinematic. And if I study dynamic, it's the study of forces applied to any body which has a mass, which is not balanced, otherwise it would have been static. Mechanics in medicine apply all the knowledge we have in mechanics at different scale, from the nanoscale to the human body scale, which in some cases is not at all nano, tissue, organs, or the whole body. So we study mechanics at any of those levels, and you have already had or will have in the next few days. I'm sorry, there has been a change in the organization of the model, and my lectures were supposed to happen in the same. I don't know if you have seen all the changes, but there have been some reorganization. So I don't know now if you have these lectures yet or not. But otherwise, in the next few weeks, you will be introduced to nanotechnology and all the applications of engineering at any possible scale. So it's a wide concept and spans from drug dynamic, what we study mainly, well, both at cell as an organ level. Tissues, an exemplar can be prosthesis, 3D printing for replacing organs. Organs level, implantable device, artificial organs, or whole body study, under robotic, as we'll see later for the abbreviation. And just to give you a framework, we may use this diagram, which I took from Proimos, a Greek professor, which I attended a master in Greece in 2012, and Proimos was bringing this diagram to try to put together biomechanics, saying that mechanics is the study of the three things that I mentioned before, and when you merge it with biology or medicine, you arrive to biomechanics, which actually may be used to study two things, physiological or pathological conditions at all the levels I described. Physiological means the study of the normal behavior, a system which is not affected by any pathology. So when we apply biomechanics in the sport domain, we aim to increase the performance of a professional runner or whatever it is. So this is application of biomechanics in a physiological field in which we study physiological movement, loads, and forces, which we can also study in a pathological condition. And perhaps that's, I will give you some exemplar, and Luis will give you, my PhD student during the last half an hour today, will give you a seminar on the activities doing about human balance associated with the sleep quality. So this is an application of biomechanics in pathological conditions. In both cases, we can work on task-oriented movement, load, and forces in occupational medicine, everyday activity, or sport, as we mentioned, because you can do that with the physiological condition subject which just you want to improve the performance, applying engineering, or it can be a rehabilitation task in which we are trying to apply knowledge coming from sport in order to recover a functionality which has been lost for any reason, from limb amputation to brain injuries. This is a typical example of application of mechanical principles, this is static, to the study of human body. So in this case, this is a numerical exemplar that I normally give both to undergrad and postgrad, which says, look, assuming this is your arm, at this point, this joint will have the following forces. So the force which is given by all the weight of the forearm, which is applied here, but then there is the contraction of the muscle, which is applied exactly in the point in which the biceps muscle touch the forearm at the ulna level. That's where the tendon brings the muscle to the ulna. Now, if you want to study the effect of those two forces, you can already apply a concept that you may have from the study of mechanics in your undergrad. So there is a balance of forces, a balance of momentum, and we apply the same concept in order to understand, in this case, what is exactly the force that we need to oppose to hold this ball in a static position. Why this is relevant? Because if I have to design a prosthesis for a patient which lost a limb, I need to know, given the dimension of patient body, what is the strain or stress that this tissue will need to suffer in real life. So this is a typical application of biomechanics applied to prosthesis. Okay, so if you follow this exercise, it gives you the typical information you get in a problem of static. So this is the force that you oppose, this is where the joint is, assuming this is very firm, and then there is the weight of all the arm plus the weight of the ball. And because this ball is far from the joint, there will be a momentum which will be higher than the one you have to oppose, which means that this force will need to be far higher than the gravitational force, the weight of the ball. If they were in the same position, so the momentum was null, then the two forces could have been perfectly the same. And the fact that this is positioned much closer to the joint than actually the weight we are trying to lift, it means that our arm has to hold something which, in this case, will be about 10 times the weight of the ball. So if you are holding a ball of 10 kilograms, your force applied here will be the same that you would apply to hold something which is 100 kilograms if it was put in this position. And that's true for the majority of human bodies. So we have every time situations like that because they are easier to control. So if you apply a force here which is 10 times the weight you need to hold, then this will make the control far easier than if the situation was in the other way around. If you apply a force which is 10 times bigger than a weight you need to control, and if the controller was there, this would have been much more difficult to control. I'm trying to plan seminars for my module, and I want to bring a controller engineer, not necessarily from medicine, which will give us an induction into control theories, if you don't have it yet. And this is a classical problem of control. If I am in such a situation, the controller is far easier to be designed and maintained. It's far more stable. Okay, here there is the mathematical solution of the problem. So if you like to try yourself, you have all the solutions. What we need in this moment, it's perhaps the conclusion. So as you see here, the force that our biceps is opposing to the weight of the ball is about 9 times bigger, because 9 is the ratio between this exercise, the 40 centimeters and the 5 centimeters, which are the distance of the forces from the joint. So there is a ratio between those two distances, which is actually giving a factor out which is proportional to the weight you need to lift. Every time you are in such a situation that you apply the force closer than the real weight, you are in similar situation, which means that if I was taller and my arm longer, the force I would have to be applied in order to hold the same ball would have been higher than if I am shorter and with the shorter arm. So that's also the reason why in some sports the physicality of the athlete is fundamental. If you see all the champions of ring, the Olympic disciplines, they're never taller than that, because being smaller makes the mechanical and dynamical aspects of sport far more easy than if they were taller. So there are biomechanical reasons, which if you know, you can also plan properly anything, training, the design of a bicycle, the applications of those principles to everyday life, both for physiological and pathological applications, are in the remit of biomechanics. For instance, this was the static position, assuming the arm was exactly at 90 degrees from the forearm. What happened, in your opinion, if I am in this position or in that position? So if I'm not at 90 degrees, when do you think you need to make a huger force in order to lift the same thing? So if I want to hold this chair like that, I will make a force which is proportional to all the principles we mentioned before. In your opinion, do I need to make more force when I am in this position, in that position, or in this position? Yes? This position?
Is it when you're out at a 90 degree angle? Not that, this one?
Not exactly. And look why. What happens here, is that the distance between the place in which the force is applied and the joint, it's closer in this position than it will be in that position. Well, no, it's closer in this position than it is in that position, meaning that this factor alpha in this condition is huger than that. So basically, it's not the same. The force that you do when you move from here to there is different than the one you oppose when you are at 90 degrees, which is different than the one you oppose when you are above 90 degrees. And those are principles. Again, if you work out the math, which is not trivial, you have different backgrounds, but if you sit together, you can do it easily. Those are things to consider, because you can never design a prosthesis just considering the static position. You have to consider that our body is never completely symmetric, and in different positions, especially the momentum, will change. So it's never appropriate to lift the weight in that position, because this will completely destroy my spinal cord. But if I am in this position, I avoid the momentum on my spinal cord. And this knowledge has an impact on labor medicine, working medicine. So giving prescription on how to lift the weight. It's a classical application of biomedical engineering in working medicine. So it's such a wide field that it's impossible to recall all of it in only 1 hour. But just I want to give you an impression. Here it is another exercise which try to explain the importance of patella, which is the rotulum, also known as patella, this small bone that we have in the knee. And because of that bone, the muscles is attached here, while actually the reaction of our body, if you sit in this position, is applied there. Now, because of this disalignment between the 2 points, so without patella, our force would have gone here and not there. And because of the patella, what really changes is the degree between the force we apply and the reaction on our body of the weight of our body on the knee. And because of this small difference, only 10 degrees, you will see if you work out the math that what actually we do is applying a force which is much less than the real reaction. So this is the reaction. In a vectorial planar representation, it means that the magnitude of this arrow is bigger, is proportional to the magnitude of the force. So that's our force, what I apply in order to maintain my body in this position. And because of the patella, which means because of this different angle, this is smaller than that. If the 2 angles were the same, the blue and the green would have been exactly of the same magnitude, meaning that the force I should have applied to hold myself in that position would have been exactly the same as my upper body weight. If you work out the math, the difference is in the order of about 15–20%. If you are in my shoes, about 80–90 kilograms, 10% is not trivial. It's about 10 kilograms more or less. So the way our body is shaped make completely different the forces that we can apply. So the reaction, what I need to sustain as a weight against the flow, it's about 15% more than the real force actually my body is applying. So in this case, the rule of patella is to minimize the balance of forces along the vertical line. Again, if you work out the math, but I leave it to you because I don't want to offend your intellect, work out the math and you will see what it is the rule of patella. So those are small exercises that I normally use in the undergrad in order to introduce undergrad students to the biomechanics. Few animations. This one aims to explain the rule of the meniscus. You know what it is, the meniscus? It's a cartilaginous surface which is between the, which is into the knee joint. What do you think it is the function of meniscus? You heard the football players know that we broke meniscus many times. What is the rule of meniscus in your opinion? Come on, you were ignoring the rule of patella till this morning, so it's fair enough if you don't know why we have a meniscus, but yes, what do you think?
It separates the patella from the tibia.
Patella is completely free. There is only a ligament, but the meniscus is our closed part, mediolateral, and that's the meniscus. And then there is a ligament to patella. No, the meniscus, this cushion. What's the purpose?
It cushions.
It's a cushions. It's a cartilaginous tissue, so it's different than the bone. They are fairly similar, but in cartilaginous tissues there is more water, so it's also more slippery as surface. Without the meniscus, the two bones, when they move together, they would have produced much more heat than it really happens because of the meniscus, because there is water inside and the dissipation of the heat it's eventually faster. But there is also a mechanical reason. This animation made by my friend Marco Sorrentino, it's exactly that. Let's imagine the upper part of your leg would have touched the lower part in one position. This would have been the damage you create because it's shaped as a half a sphere, which means that the weight would have touched the below surface would have been only in one point, which would have increased pressure, which would have damaged the underlying tissue, especially during motion, because if you rotate this, as we actually do with the leg, that's exactly what would have happened, that you would have damaged the underlying tissue. Now, because of the meniscus, that's actually what happened, that you increase the contact surface. And that's what happened in many other joints as well. But the knee is fundamental because at the knee, I'm already applying almost the majority of my weight. And when I run or when I hold something on my shoulder, this is insisting on the knee. So the knee, it's a very important as the ankle as well, but in the knee, it's even more the weight that the knee has to suffer. So giving such a cushion means that we are increasing the contact surface. And when you increase the contact surface at the same level of forces, what you are increasing? You are decreasing the pressure. The pressure is force divided by surface, isn't it? So this is one of the functions of patella. And in this other animation, again, this comes from the book of Proimos, and those animations from my friend Marco, which is an expert of use, is the fact that the way in which we move the knee, it's very peculiar. There is not only a rotation, but while rotating, the knee is also, the upper leg, it's also shifting. Because if you take off the shifting, that's exactly what would have happened. That during the rotation, the upper part would have been going out of the lower base. Let's see this animation. Here we have the motion decomposer. So this is all together. You don't even notice it. But apart the rotation around about this point has gone from this position to that position. Let's see it again. Apart rotating, this is going back, sorry, the other direction. So apart rotating, it's also moving back. If I want to decompose this movement, That's what you see. First rotation, and then translation, and then the final rotation. Those are the same movement, just we changed it in this animation their orders. So we programmed the motion, and then we changed the time. The final result is the same, we are about in the same position, but this is demonstrating exactly what is the real motion that our knee does, simultaneously, so you don't notice it. So it's rotation and translation, and shifting. Again, that's another typical application of kinematic in medicine. If you don't study the dynamic property of human body, you will never be able to properly design a prosthesis, especially in these cases for orthopedic application. That's not the only case. We also produce, I don't know, prostheses for the valves into the heart. And those valves, they actually never stop. There are valves that open and close every time our heart beats, which means that the dynamic of those valves is crucial. So the study of dynamic in medicine is fundamental for many activities. That's another exemplar of how the shape of our bones increase the degree of freedom of our movement. So if our bones and our knee was not shaped as it is actually, then you would have not had the possibility to move it. Only a spheric shape would have given a certain degree of motion, but the fact that there is a sphere which goes about for 3/4 of the knee and it's slightly disaligned from the axis has a lot of good mechanical properties. So our body, evolution unless you're not a creationist, the evolution brought us to have a very optimal structure when it comes to our skeleton, which is ideal to support our motion being in vertical position. Okay, few reflections that, again, if you enter this field, are important. Here another animation to explain the cruciate ligament, which is the one which keeps together the knee. It's called cruciate because the two ligaments make a kind of cross. Okay, and in this animation aims to demonstrate the utility of that. So being cruciated, you can have a wider angle of rotation. This is going in both directions, but in reality the patella stops your knee about half a movement ago, so you cannot move your leg in both directions, and that's also another function of the patella. But you saw the possible movement on the back at least, and the anterior also movement. But what if instead of having a ligament which was cross-shaped, we would have had something else? As you can see, the degree of freedom is completely different. You would have had distal movements, so the two bones would have also been movable in this direction, which is not ideal, because if I go out of the down part of the joint, I fall down. So we need also to maintain in place the knee, because of the rotation I showed you before. So the functionality of the cruciate ligament is important. And when you study the replacement of the ligament, when you study the kind of material you want to use to replace a ligament, those informations are crucial. The dimension, the shape, the material, those are all things that biomechanical engineers take into consideration when they have to design a replacement for a ligament, for instance. I focused on the knee, but the same things applies basically to any other joint in our body, some of which are far more complicated than others. This is exactly what I was trying to explain before. If I just lift something with my arms, the position I do that will change completely the forces that applies on my lumbar scales. And if I don't pay enough attention, I risk to seriously damage my lumbars. Now, in our everyday life, perhaps this is not a prominent problem, especially in your young age. But if you are a worker doing every day this kind of motion, having this knowledge is important. And we can apply this knowledge in order to design proper protection and ergonomy of a motorbike, ergonomy of whatever else. So those are the kind of applications of biomechanics in working medicine. Okay, I don't have an exemplar of applications in at cellular or tissue level, but you will have other colleagues which they work in this field more than I do, so they will be more able than I am to show you that. And you have a whole module of biomechanics, which Neil is giving, I think, in next term or this term, I don't know. Now, this is an exemplar of how we can apply the knowledge of biomechanics in sport medicine, or just to increase the performance of a professional athlete. What do you think is going on here? Which one, in your opinion, is using the best technique? Which of the four? Yes.
Second.
Huh?
Second.
The second. Why the second?
I think she's exerting pressure on both the legs. I'm not sure.
From the mechanical point of view, jumping high, what does it mean? What are you doing from the mechanical point of view? Eh?
I didn't get you.
You didn't get me. Me neither, especially in the morning. What you do when you jump, technically, from the mechanical point of view, you are lifting your center of mass, which if you were perfectly symmetric would have been the same as center of body. But because we are not perfectly symmetric, the center of mass is disaligned by the center of body. But what those four athletes are doing in a different manner is positioning their center of mass against the shaft. When you jump, the force and the power you need to jump, it's only a function of how high it is your center of mass. Because if you work out the math, you will see that the only vertical force which you should take into account, assuming that all the other forces are not important, as the aerodynamics and things like that, which in this case it's a fairly good assumption. The only force which you need to take into account if you work out the math is how high is the position of your center of gravity, center of mass. And with an animation, I can show you that more or less this guy is bringing this center of mass above the shaft. Fine, if you can do that, do that. But if you have to compete, trying to pass above your body, the point is not where your center of mass passes, but it's where you can pass. So if this guy improved this technique, could have been jumping much higher. In the second case, the position of the body this athlete is assuming, so it's the technicality which is behind the execution of this jump, it's much lower because she was very good in arcuating her body. And if you sum all together the parts of her body, you would have a center of mass about in this position, which is below her body, but still very close to the shaft. So on so far, this is the best jump, because this athlete has been able to move her barycentrum below the shaft, and she's going above. So that's the best execution, because she had to consider and apply forces to bring her barycentrum only here, not above, and the distance of 20-40 centimeters can make a difference, especially in Olympic Games. We are talking about a few centimeters to beat a world champion record. So the execution is fundamental, and the knowledge of physics in this execution is crucial. The next time you jump, keep in mind those slides. So this is an exemplar of how biomechanics can serve medicine when it comes to professional sports. This is another exemplar. Cycling has been significantly growing in the UK after the Olympic Games. There is a lot of applications of engineering over there. So the way the power you pass to the pedals, it depends very much from the position of the pedal. So are you pushing enough when you are in this position or in that position, or what? Pushing too much here could be useless because all the force would be absorbed by the rigid body which is behind the pedal, so it's useless. So perhaps here you can rest. And then this is when you have the maximum transfer of power to the bicycle. So that's when you should focus if you are a professional athlete. And here if you can also rise it up, but this is also without a goal, so just pushing down. So having the knowledge of when you have the maximum transfer of power to your bike, perhaps it's irrelevant for you if you come by bike every day to the university. But again, if you were trying to compete and even as a fraction of a second becomes significant, then this is becoming really important. And how do we do that? This is a gate lab. You will see applications from Luis and Neil in the next few weeks, Luis in a few hours. Those are markers, which those particular cameras are infrared cameras, and those markers can reflect the infrared positions. And by positioning them on the leg, you can actually measure exactly this kind of position, and putting few force sensors on the pedals, you have the combination of the two information. That's biomedical engineering applied to sport. We have a gate lab. You will see the application of the gate lab in a few minutes. And by using our knowledge, we can improve the performance of the athlete. Dynamic swimming. This is another case in which aerodynamic principles can increase the performance of the sport. This is rehabilitation. For several reasons, a patient may need a rehabilitation. It can be an ictus, which devastated part of the brain, which was the one we use to execute a particular movement, or could be related to memory, whatever. According to the intervention which to the problem, medical problem that the patient had before, the therapeutic intervention, the rehabilitation intervention will change. And the design of those interfaces and eventually video game, in order to be sure that the engagement of the patient is very high, because engagement of patient in rehabilitation is fundamental. So all this knowledge goes from the robotic side of it to the design of the software, which is meant in order to increase the attention of the patient in a closed-loop strategy approach, which is typical of biofeedback, in order to increase the attention of the patient. Because if you just do an execution like that, this is absolutely useless. But if you focus very much and you understand what you're doing, this is useful, especially when it comes to rehabilitation due to neurological problems. Because you need to rebuild the pattern that the brain has lost. So if you have, for any reason, lost the functionality of that cortical area, which has an influence on the execution of a movement, what we do with rehabilitation, we try to train the surrounding part, because our brain is plastic. That's something on which we will be back tomorrow about noon. What we try to do, we re-educate surrounding cortical areas to the execution of this movement, possibly because an ictus has damaged or a trauma has damaged that cortical area of the brain, which was deputated, which was the one responsible for this particular movement. Now, to do that, it's not the physical part of our body which has lost the functionality, but it's, in a way, our brain which does not know anymore how to control it. When you want to do this kind of manipulation, which is not a body problem, but it's a brain problem, so it's not into the muscle or the joint, there are rehabilitation interventions meant only for joint and muscles. But if the problem is to re-educate surrounding cortical areas, then the attention of the patient is crucial. And that's where the majority of biomedical engineering interventions are done in the field of rehabilitation. Clear? Questions? Comments? This is just to give you an impression, an idea of different implantable, passive and active, well, this is all passive devices. But then we will see later on, in about 40 minutes, an overview of an active implantable device, pacemaker, which is often associated to biomedical engineering because it's one of the main innovations we brought in medicine in the past 60 years. Just to give you an overview, according to the position of the body, there are different designs for passive device for spinal surgery. So it's a huge, huge, huge field, as many other fields. And those are typical prostheses for sport, in case of loss of limbs or arms. And this is an application of exoskeleton, robotics for exoskeleton, either for rehabilitation purposes, no, I don't see any. But this is all in order to replace a lost functionality with the robotic approach. Exoskeleton or robotic arms. Eventually applications for rehabilitation, but I'm not sure what application was behind this approach. Okay, this closes my second part of the lecture, which wanted to give you an induction into the wider field of biomechanics. You will have a module of biomechanics, which will give in details all the required knowledge which you need in order to use biomechanics in medicine. Questions?
Yeah, regarding that, the part of the brain that was dormant,
Yeah.
the movement, I didn't see that anything was connected for her to aid her movement to the brain. So how does that work? Like, it was just on her hand.
The arm was different, so in this case it was a rehabilitation arm. So it was not
It was just a
that we
muscle.
were controlling the motion through the brain, which would have been called brain-computer interaction, which is the field in which Professor Christopher James is very expert. I'm sure he has already given some induction into the brain-computer interaction, which is actually the other way around. With your brain, you are trying to control a wheelchair or an arm, a robotic arm, or whatever. This is brain-computer interaction. In this case, rehabilitation is trying to do exactly the opposite. I'm trying to convince your brain to train again your brain to do a movement. That's something that you learned over years since you were a toddler. You learn how to walk by observation, then by trying, and then by folding, and so on and so forth. When you are a toddler, that's a process which takes about a couple of years to properly control your movements. If you suddenly use this knowledge, and this knowledge builds, our brain is completely plastic, so it changes physical properties and asset according to the experiences we do. I will give a short demonstration tomorrow. Now, what a toddler does in 2 years in a brain injured patient has to learn in the soonest possible time, the shortest possible time after the injury, because otherwise you lose completely that functionality. So,
Convince the brain that you can do it.
sorry?
You convince the brain that you can do it.
You convince the brain you can do it, but you have to retrain the brain, because what happens when you learn something, again, we talk about that tomorrow, is that you create new synaptic links between different parts of your cortical area. We talk about that tomorrow more in detail. If one of those parts is physically damaged by a trauma or lack of oxygen due to any possible reason, this part is damaged, and our brain, differently from many other parts, has huge problems in adjusting itself. Cell brains, once dead, are dead. The rate in which they adjust themselves is almost zero compared to other cells in our body. We have liver cells which are really able to regenerate themselves very fastly, but brain cells, no, they last almost for all our life. That's why we keep memories most likely. Otherwise, we've lost our identity. But the consequence of that is that after an injury, they are not able to regenerate themselves. So the only solution we have to teach the surrounding part to do what this damaged part of our brain was deputed to do. But it's not easy. I mean, the more we grow older, the less plastic is our brain. So if I have an injury, Now, my probability to recover probably are different than the one I would have had 20 or 30 years ago, and the same in the future. So it's not an easy effort. But the idea is exactly that. We try to teach our brain how to do something that you learn as a toddler in a couple of years, without being afraid of falling with many other good drivers, emotional drivers. During rehabilitation, you don't have all that. You only have the stress of post-trauma, plus the difficulties of doing that only a few hours per day. When you were a toddler, you were practicing non-stop. Rehabilitation is something that you cannot do 24 hours a day. So it's completely different, but that's exactly what we try to do. Teach our brain how to do something which, because of any reason, is not able to do. Answer your question? Perfect. Other comments?